It's my pleasure to announce the second speaker this morning, Simon Perdrix, on basis in diagrammatic quantum properties.
Okay, thank you. So, first I want to thank the organizers for the invitation. So today I want to talk about diagrammatic quantum protocols, and I'm going to present categorical semantics for two protocols. We consider two protocols: the quantum teleportation, which you probably already know, and another protocol which is the state transfer. And in order to this categorical semantics is based on the categorical axiomatization of bases, which has been introduced by Frobenius and Perdrix. And so by bases, I mean the orthonormal bases in a finite dimension Hilbert space. This is the mathematical point of view. But from the physical point of view, the basis, when you fix a basis, you fix the observable as well. So it means that you fix the property that you're interested in, the energy, the position, and so on. So, and it turns out that when you fix it, you also fix the frontier between the classical and the quantum world, in a sense that if you have a basis state, then this is a classical state, whereas when you have a linear combination of basis state, that is a superposition, then this is a quantum state. So, and it turns out that the axiomatization of basis that I'm going to use, which is due to Bob and Dusko, was originally called classical structure. Classical structure. Yeah. Okay, so this is a joint work with Bob and Eric Paquet. Okay, so as I said before, I'm going to present categorical semantics for two protocols, two quantum protocols, the teleportation and the state transfer. And this work is part of a program which has been initiated by Samson Abramsky and Bob Kuke with the Leaks paper, and 2004, which was called Categorical Semantics for Quantum Protocols. And it turns out that the main example, which is illustrated in this paper, is for the quantum teleportation. Okay, so here we will consider again this protocol and another protocol, the state transfer. Okay, so there are several applications for the teleportation, but an original application of the teleportation is the measurement-based quantum computation. It turns out that Michael Nielsen, when he was interested in quantum computing, introduced a measurement-only model of quantum computation. So the idea is that instead of using unitary transformations, which is the case in the original model of quantum computation, in this measurement-based model, we use projective measurements instead. Okay? So projective measurements only in order to realize the quantum computation. And it turns out that this model, which has been introduced by Nielsen, was based on the teleportation, on the protocol of teleportation. And in order to decrease the resources which are required for such a measurement-based quantum computation, I have introduced the state transfer, and I've proved that if we replace the teleportation by the state transfer, we can minimize the set of projective measurement, the set of primitives that we have to use in order to realize the quantum computation. So these two protocols are related to measurement-based quantum computation. And moreover, the state transfer can also be used in order to unify the two models of measurement-based quantum computation, which are, so on one side we have the model which has been introduced by Nielsen, measurement-only quantum computation, based on teleportation and so on, and the other model, which is also very promising for physical realization and so on, has been introduced by Briggen and Rosendorf. This is the one-way quantum computation. The idea is that we assume that at the beginning of the computation, we have a large integral state which is used as a resource for the computation. So it's a different model. However, these two models can be unified using this state transfer. Okay, so this is the motivation for studying these two protocols. So the roadmap, I will first remind you or introduce these two protocols, the teleportation and state transfer. Then we will see what is the categorical framework that we'll use in order to give this categorical semantics for these protocols. And finally, we'll compare this approach that I'm going to present with the original approach by Samson Abramsky and Bob Kuke. which was based on categorical structures instead of this axiomatization of bases. Okay, so the protocols. I think that you already know the teleportation, which has been presented yesterday. Okay.
Sorry, I missed that. Can you say it again briefly?
Okay, no problem. So, in the teleportation, so at the beginning we have here a 2-qubit state, which is an untitled state, which is shared between Alice and Bob. Then the story says that Bob is going far, far away from Alice with this qubit. And Alice now wants to transmit the state, an unknown state phi. So she wants to transmit this state to Bob. And in order to do that, she decides to apply a Bell measurement, a 2-qubit measurement, which is described by a set of 2-qubit projectors. So she applies this 2-qubit measurement on these 2 qubits, so the unknown state and this qubit of the pair which is shared with Bob. This measurement produces 4 possible outcomes, classical outcomes. So she sends these classical outcomes to Bob, and then Bob applies a unitary transformation which depends on this classical outcome, and at the end of the process, at the end of the protocol, it turns out that the state of this qubit is phi, the original state phi. Okay? So here, in order to transmit this state, we use disentanglement and just a classical channel. Okay. So the state transfer, of the protocol that we're interested in, is so it's quite similar, but the difference is that at the beginning we have only one qubit, one ancillary qubit, which is in the state ket0 plus ket1. So it's similar in the way that we want to transmit this state from this qubit to this one, and in order to do that, we apply here a 2-qubit measurement, which is a partial measurement. It means that this is a 2-qubit measurement, however, there are only 2 possible outcomes, okay? Instead of 4 in this case of the Bell measurement. Here, this is a parity measurement. So we apply these 2-qubit measurements, which produces just 1 bit of information because there are just 2 possible outcomes. And then, after the application of these 2-qubit measurements, we measure the first qubit in the diagonal basis. So we measure this qubit, which produces another classical outcome, y. And using these 2 classical outcomes, we apply a unitary transformation here. And it turns out that the state, at the end of this protocol, the state of the second qubit is phi. Okay, so we have these 2 protocols, and what we want to have is to give a categorical semantics for this protocol. The objective is to give a proof of these protocols, which are both rigorous, so based on category theory, and intuitive. And in order to have this intuitive proof, for these protocols we use graphical representation. Okay.
So understand the state transfer, so what someone gives you a phi, and at the end of the day the algorithm gives back the phi. So what is the excitement in that algorithm, as opposed to the teleportation where you actually something jumped across the Lake of Geneva?
Yeah. Okay. I see. So in the state transfer there is no non-local application for the state transfer. Okay, everything is local here because we apply these 2-qubit measurements. So
what possible application could there be, though?
Okay, the application is the measurement only quantum computation. Because the idea is that if we look at the teleportation or the state transfer, and if we don't care about this corrective step, which consists in applying this unitary transformation here, we can see that we use only projective measurements. Okay, here we use a measurement, here 2 measurements. And this is the starting point of the measurement-only quantum computation. And the next step in the measurement-only quantum computation consists in saying that if here, for instance, you apply a measurement which is not in this basis, but in a rotated basis, then you will transmit the state phi up to a unitary transformation. So you can simulate a unitary transformation on this state by modifying the basis of this measurement. This is the main application of the state transfer.
wouldn't another use of it be to physically, if you have a qubit stored in some physical medium, say in a state of an atom, to physically transfer that to a different form, say a photon of light or something, to sort of transfer the way that you're storing your qubit physically?
I'm not sure to see what you
Yeah, it means to transfer the state from one system. But what you do is transfer the state from one system to another.
Yes.
So it says.
Sorry, I understand. Okay, sorry.
And do I understand correctly that this kind of allows to make quantum measurement kind of without destroying the state? So you preserve the state and do measurement.
So no, it modifies the state.
Yeah.
But this measurement is not destructive.
Yeah.
So it means that we can reuse the qubits. We can
Yeah.
act on the qubits after the measurement. But this measurement is.
I
So
understand.
you apply. You
Yeah.
have two
Yeah.
projectors. So you apply a projector and
But then
change
you-
the state of the system. Of course.
Yeah.
But when you finish, you now know X and Y. Does that knowledge tell you anything about psi?
No, you have no. X and Y are just random bits. There is no way to have information about phi in this using this program.
So it allows kind of make statistic just with one qubit, right? So you can repeat this measurement and keep the state, something like that.
In order to do what? What you
Kind of you can probably make statistic. You just if you preserve your state and you can repeat it
yeah, but
quantum measurement on that.
But
X
the
and Y are
measurements,
random.
the outcomes
because you
of
know-
the
Yeah,
measurements
sure.
are not related to the state. In fact, they are just random bits.
Yeah. Okay.
So you have no information about the state if you
Yeah.
repeat the process.
But you get like random. Yeah. So it has to be
Source.
random. Yeah.
Okay. Okay, so we'll consider these two protocols. So now the categorical framework. So I start with the very beginning, so I think that I can go very quickly through this part. So we'll use symmetric monoidal categories. So we have, no, it was not symmetric, but anyway. So we have this category, so we have this bifunctor tensor, which satisfies some coherence conditions which are not represented here. I just want to say that an example of such symmetric monoidal category is the category of finite dimension Hilbert spaces. So the objects are finite dimension Hilbert spaces, and the morphisms are the linear maps. The tensor is just the tensor product, and the unit is the one-dimensional Hilbert space. Okay.
Looking at that, I can't see them seeing that in the braided monoidal category. Where's the crucial difference between?
Because the difference is that we have this
Certain coherence conditions.
yeah,
coherence
coherence
conditions.
condition.
Sigma squared is 1.
Yes.
But they're different signals, because one is sigma AB and the other is sigma BA.
Sigma AB times sigma BA is 1.
Anyway, so it's in coherence.
Not really. Okay, so it's just the interesting part is we have talked yesterday about dagger categories. So here it's dagger symmetric monoidal categories, which have been introduced by Selinger. So here the idea is that we want to be able to talk about unitary transformations. Okay, unitary transformation is an important point in quantum mechanics. So, and in order to do that, we'll use dagger symmetric monoidal categories. So it's a symmetric monoidal category with a functor dagger, which is identity on object, which is contravariant, so and which preserve the monoidal structures. So we have all this coherence condition. I have to say, so this is involutive and so on. Okay. We want that. I can go to the details if you want. Okay, so an example of finite dimension Hilbert spaces. An example of such a dagger symmetric monoidal category is the same example as before, so the category of finite dimension Hilbert spaces, where the dagger, F dagger, is nothing but the adjoint of F. Okay? So F is a linear map, and F dagger is the unique linear map which satisfies this property. for any V and W. Okay? So, so when we work with symmetric non-unitary category, we have a graphical language, a rigorous graphical language, which has been extended by Selinger to the dagger symmetric non-unitary categories. So the morphisms are represented as follows. So we use oriented wires, and we use these boxes which are asymmetric, these weird boxes. This is an important point for the following. So the identity is just represented as follows. Here, this is the composition tensor product. And in the dagger symmetric non-unitary categories, we have this representation of the dagger. So the idea is that F dagger, the morphism F dagger, is represented using this box upside down.
Is there a B and an A one way around that?
Yeah.
No. No, because here it's F dagger.
No,
no, he's right.
So, okay, so we start with F, which is from A. So we have F. We have F dagger, which is to A. Okay, and this one will be represented with the box upside down. Okay, so we have this graphical language for dagger symmetric non-unitary categories. And, okay, so as I said before, one of the objectives here is to be able to talk about unitarity. So, for instance, we would say that a morphism F is isometric if we apply F followed by F dagger, we have the identity. Okay, this is the isometry condition. And the morphism is unitary if both F and F dagger are isometric, or in other words, if the inverse of F is F dagger. Okay, so we have this definition of unitary morphisms. Okay, so another important property in quantum mechanics is the no cloning theorem, which says that there is no quantum evolution from H to H tensor H, such that for any state phi, F, the image of phi under F is just two copies of phi. Okay? So it's not possible to duplicate the quantum state. Okay? So this is the no cloning theorem. However, it's possible to copy. Okay? Cloning is forbidden, but copy is allowed. So what is a copy? If you fix a basis of the Hilbert space, so an orthonormal basis, like this one, then you can define a linear map, which is defined as follows. So for any basis state, you duplicate this basis state. And here, this operation is called a copy. It depends on the basis. And it turns out that such an evolution is allowed in quantum mechanics.
So why it's not cloning?
Yeah. We'll see an example. So, for instance, if we fix the basis, which is the standard basis, so if we consider the cubic case, so here this is a two-dimensional Hilbert space, so the basis that we consider is just Ket0, Ket1, okay? So, we define the copy in the standard basis, which associates with 0, 0, 0, and 1, 1, 1. So, can do it, and it turns out that this is not cloning, because if we apply this linear map to an arbitrary state, alpha 0 plus beta 1, then we obtain by linearity alpha 0, 0 plus beta 1, 1, which is different from two copies of the original state. Okay? So this is not cloning. It's just a copy in a specified basis. Okay, so we can define another transformation, which is the delete. So which associate with any basis state, just one. So this operation is also basis dependent. And we can see that if we apply the copy, and then if we delete one of the two qubits that we obtain, if we apply this delete on one of the two qubits that we obtain, then this is the identity. Okay, this is what I call this operation delete. Okay, so cloning is forbidden, however, we can define this copy and delete. And the important point is the dependency of this operation on the basis that we choose at the beginning. Okay? And the interesting point is to see that this, in fact, we will use this dependency in order to characterize the basis. Okay? Here we have two operations which depends on the basis, and we will use this dependency in order to characterize the basis using this kind of evolutions. This is the idea of the dagger-Frobenius structure, which has been introduced by Bob Good and Dusko Perdrix.
Are evolutions normally invertible?
Okay, so this one is an isometry, so it's okay.
It's not invertible.
No, it's not invertible, but it's an isometry. So.
Can be extended to a unitary. Usually, you would take an ancillary qubit in some random state.
I see.
That's not an essential part of the.
I see.
So you can always extend this.
I see.
So there is a physical meaning for this one, okay? Because you can adding ancillary qubits and so on. For this one, no. But however, we will see that we can use it.
There's a no deleting theorem, and then you sort of erase against another, and you do basically the same trick. But it structurally is a different thing. You use different part of the structure to say that you can't do it. So.
Yeah, because there's this whole thing about reversible computation.
Yeah, sure. Yeah.
I see. You're saying you can add that on.
You can always extend an isometric.
Okay, so dagger-Frobenius structure. So what is dagger-Frobenius structure? So for given object A, we have two morphisms, delta A from A to A tensor A and gamma A from A to I, which forms a co-commutative commanoid, and moreover which satisfies these two equations. So the first one is the isometry, and the second one is called the Frobenius equation. So graphically, if this morphism delta is represented as follows, so the idea of the copy, okay. If the delete is represented as follows, so we have one input and no output, the dagger of delta A is represented as follows, and here this is the dagger of the delete, which is in fact the state initialization. Okay, we have nothing at the beginning and we have the state after the application of this move. Okay, so if we use this graphical notation, then the coherence condition can be depicted as follows. So here we have the commanoid equations, associativity, commutativity, and the additional equations are this one and this one. So here we have the isometry, so if we apply the copy and then the dagger of the copy, we obtain the identity. And here another equation. I have no physical interpretation for this equation, but it's a very interesting, very useful equation. So we have this one, which says that if we apply here the multiplication, that is the dagger of the copy followed by the copy, this is equivalent to this thing. This is the Frobenius equation. Okay, so here we can define this dagger-Frobenius structure, and I said that we use this kind of structures in order to have an axiomatization of bases, and in fact this is, we have this property which confirms it, which is that we've considered the category of finite dimension Hilbert spaces. It turns out that there is a one-to-one correspondence between the orthonormal bases and the dagger-Frobenius structures. So here, using these dagger Frobenius structures, we have an axiomatization of the autonomous basis. Okay, so when we have a dagger Frobenius structure, we can define some specific morphism. We can say that F, morphism F is a partial map if we have this property. It is applying F before the copy is the same as applying F twice after the copy. F is a permutation if F is a partial map, and moreover if we have this property. It turns out that permutation is nothing but a commanoid homomorphism. Okay, so but we use this permutation. We say that this is a permutation. And moreover, we say that G is a phase map if we have the following property, which is that we can move G through the dots. Okay, it's very different from this one.
Why do you call it partial?
Okay, so this vocabulary comes from the original name of this dagger Frobenius structure, which was classical structure. And here, if a map is satisfying this equation, then this is a classical map, which is not total, because if the map is total, then it satisfies this one.
By classical map, you mean the map on the basis?
It's
Yes,
on
the map which transforms basis states into basis states.
It acts like a partial function on the basis vectors. And
What happens in infinite dimensional Hilbert spaces?
I don't know.
It does, in infinite dimensions it doesn't work because there are no infinite dimensional Frobenius algebras, so there's no hope of getting it to work directly.
I wonder what a phase map would be. What does a phase map do on an orthonormal basis?
A phase map do nothing on the basis state. It's just add a phase. Okay, so in other words, it's a diagonal. If you look at the unitary representation, this is a diagonal matrix. Okay, just add some phase on the basis states.
So can I just go to the previous slide?
Yeah.
So it's just a comment that last condition of that the no loops rule, the asymmetry, it places people like me in a bind, because if I want to use this terminology in the TQFT context, I'd like to have terminology for something which doesn't satisfy that rule. Then I would have to have a non-isometric dagger Frobenius structure. It's sort of, you close the door for anyone else to enter into your party now. Because
well, I think there's about 3 other names around for that thing.
Yeah.
Some people call it normal, some people call it special. I think Joachim Koch calls it special.
So I say you should also call it special.
Oh yeah.
Because you've sort of vocabularily shut everyone else out on the party.
Yeah.
Anyhow, it doesn't matter.
It's what it does. Well,
Yeah.
typically in like topological model filtering, you don't want this thing.
Exactly.
You don't want these things.
Yeah.
So why do you want this Frobenius condition?
Because it works.
What works?
This property, which is that here we have these structures, we have exactly characterization of the basis, the orthogonal basis.
The origin of that condition was when they axiomatized the category of relations. So it's sort of imposing some classicality. That's the best interpretation I can have. So when they axiomatized category of relations, that's what they needed. So which,
it comes down to sort of transitivity of equality. If you actually look at what it says for relations.
So what, in any category relation you have this Frobenius structure?
yeah, if you want to, like, there is this Carboni-Walters axiomatization of the category of relations. That's like the key structural part of the whole thing, which really characterizes relational calculus.
Your phase map, don't you need some extra condition? It seems to me that if G was a phase map, so just multiplied by e to the I alpha or something on your basis vectors, then you could multiply that by like, the number 7. And because these are all linear equations,
Yeah.
7g would still be... But then that
Yeah.
wouldn't... That isn't a phase anymore, that's changing the magnitude of things.
So
So
in this case, it's not a unitary.
Yeah.
So
It's just any diagonal...
You can say that you work with a
It's just-
unitary phase, and in this case, there is no...
So I think in this case it's exactly... Phase map, as you find it there, is exactly any operator which is diagonal in the basis defined by the Frobenius algebra.
For practical protocols, you would restrict only to unitaries anyway. That's the only thing you can do. So if you take it on a qubit, the unitaries, you exactly get the phases here.
So if you want to call it a phase map, it would be good to also say that it has that property and it's unitary.
Yeah. It just turns out that this is the only thing we need in the derivation. So that's...
Yeah. So you're to the sort of more precisely, the property says that if you in FD Hill, if you take an object A, then orthonormal bases for A are in one-to-one correspondence with Frobenius structures on A.
So all Frobenius structures arise from such a copying of bases, basically. That's what it says. They all arise in that way.
Yeah. So you could generalize G to be a phase map from A to B if you have Frobenius structures on each.
Yes.
No.
At the moment, we just have to find just one thing. But yes, we can extend it. But we can extend it to the case where G is from A to B. Okay, so another interesting thing to do with this Frobenius structure is to do this thing, that is, we apply the dual of the delete, so we create a 1 qubit state, if we work with qubits, this is 1 qubit state, then we apply the copy, and we obtain a 2 qubit state, and it turns out that, so we will represent this state as follows, this morphism as follows, and it turns out that we can prove that for any h, and any basis or any Frobenius structure that you choose, in the case of the finite dimension Hilbert space, you obtain an Untitled state if you realize this construction. Okay. So you can use this construction in order to create an Untitled state. And in the example that we have seen before, so the example of the standard basis, if you do this construction, you obtain this Untitled state, this Bell state, EPR state. Okay, so now we are ready to look at the categorical semantics of the teleportation. So here we have the teleportation. I presented it at the beginning, and the first things to do is to look inside this box and try to express the projectors, Px, using the graphical notations that we have seen before. And it turns out that maybe the first thing to do is here we have this 2 qubit state, this Untitled state, and we have just seen that this 2 qubit state can be represented as follows. Okay, here we have an Untitled state, which is nothing but this one. Okay, so here we have the Untitled state. And for the projectors, we can use the dagger, okay, the adjoint of this 2 qubit state, so we have it here, and then this one. Maybe I have to explain it. You have seen the Dirac notations?
Yeah, briefly. So it's a cat bra, you can say a cat bra.
Yeah, it's cat bra cat. Okay. Anyway, so the idea is to look inside this box and decompose the projectors as follows. Okay, for each x, there is a unitary transformation such that each projector can be described as follows. Okay, so we obtain a representation of the teleportation in our language as follows. This is the translation of the teleportation in our language. So now we want to prove that this teleportation is equivalent to the identity from here to here. Okay, so first remark, in the teleportation we don't care about the state of the qubit after the measurement here. So here we don't care about this part. Okay, we just want to know what happens between this wire and this one. So we can
There's something that's puzzling me is when you phone the guy the other side of the lake, you're telling him what X is, are you not? So where does that observation come within the dotted box?
So here you have 4 possible projectors.
Right.
Okay.
Yes.
Corresponding to x0, x1, x1, x equals to 0, and so on. So here in fact you apply one of the projectors. Here.
But how do you know which one to apply if you haven't done the measurement?
Well, you don't choose, it's the measurement that chooses.
Yes.
So it tells you which one you applied.
Okay, so here this x is produced by the measurement. Okay, it's a random x which is produced by the measurement. Okay, and this x here comes from the classical communication, which is not represented in this diagram. But this x, but the classical communication says that this x has to be the same as this one.
You mean X is a choice of one of 4 possibilities?
Yes.
But it's made by
this x is produced by the measurement.
What are those 4 possibilities?
0, 1, 2. No, the 4. Here we have 4 projectors. Every projector is a projector on a Bell state. Okay, 4 Bell states.
Just the 4 Pauli matrices you can choose.
Yeah, so these UX are the 4 Pauli matrices basically. So they make up a basis, they make up a basis.
But they're supposed to be unitary, right?
Yeah, they're
Yes.
unitary.
There is.
But Pauli's
Here
aren't
is unitary.
What?
Pauli's aren't unitary.
Yeah, they are.
Pauli's are unitary.
Oh, okay. Maybe. Oh, I see.
But Simon, this sort of departs from the sort of standard idea, which is that you present your protocol in the form of these diagrams, and then you read it. Time goes from bottom to top, and it gives you a recipe of how you perform the protocol. So you're reading up. First, it tells you to start with a state on the left, and then produce an entangled state. So you do that, and now you've got to perform some unitary UX, but you don't know how to do that.
No, but
So it seems to depart from the conventional.
No, this is a representation of the projector.
yes, you have to see that in this box, this is just the measurement which is applied. Okay, just one application, and it turns out that you can interpret it as the application of a unitary transformation, the application of this.
Even though you personally are never applying a unitary transformation, you're just performing a measurement.
Yes.
Yes.
Yeah.
This is by closeness of your category that you know you can represent any linear map like that, so the projector will
Of course, but I don't.
I mean, you can regard it as a game.
Yes.
You
Which
can
one do you need to
yourself
fill in
on the
to
world.
make it work?
Yeah, and you
Okay.
do this, and then the world does that, and then you do
Yes.
that in response to what the world does.
But this is exactly this uneasiness that I always feel about this, because here you go through this in the direction of physical time. Then you come to a point where you don't know what to do. And then Bob says, okay, this is just a representation of something. Actually go out there and make your measurement. And then you will know later on what you did before.
But I think
that's a little crazy.
I think he's got some more to say though. He's going to introduce some more things.
I am. No. So,
The Frobenius algebras haven't got into it yet, so give him a chance.
Yes, we will use it to prove
But that the third UX on the right is something you do. You do choose that.
Yes.
is that because it's not in a dotted box?
So
Yeah. So it's
Yes.
you
So,
do
yeah,
rather
the
than
idea
the
is
universe
that
does to you.
Okay, so this x is given by the measurement. It's a random x which is given by the measurement, and the classical communication here is just represented by the fact that you use the same x here. You apply the corresponding unitary transformation here. Okay. Okay, so as I said before, we can remove this part of the diagram because we don't care about the state of these two qubits at the end of the teleportation. So we have just this one. Okay, this is the starting point. Okay, so now we said that this notation is a shortcut for this one, so we just replace it by the definition. We obtain this. And now the key step is to use the Frobenius equation from here to here. So the Frobenius equation says that whenever you have this, you can replace it by this. Okay. So here, this is what we do. Here we recognize this thing, so we replace it by this one. And we obtain this diagram. Now we just have to use the monoid and comonoid properties, and we obtain the identity here. And now finally we use the fact that ux is unitary. So ux diagonal followed by ux is just the identity. And here we obtain a proof of the teleportation.
I have a question here, because it seems very clear to me that you need the Frobenius rule to do the yanking. The way you talk about this quite often, you never mention, at least in the first step, the Frobenius.
No, because you actually don't. You can just use the compact structure from the start. This is like compact, which we saw before, the duals. You can just do duals and one. So I think what the reason he gives this is to emphasize a connection, I think, with the next protocol he's going to describe. But you really do,
Yes. And why is in your protocol? Why is it important? Here we have these arrows on all these strands, and the arrows all run in the direction of physical time.
Yes. At the moment we don't really use the arrows, but we use it after. And you're right. All the arrows are in the.
That's mainly the point. If you want to stick to this sort of forward flow, then you need Frobenius. And you can't do it, that's the whole point.
That's a good point. I wanted to hear this actually. Okay, let's see this.
It's now to see that the arrows are all flow. So you don't have this avoids the need to have this backward in time type of interpretation. So you need more structure to be able to do that. Frobenius is more structured than duals.
Yeah, I'm going to compare this approach with the original.
Okay, thanks.
So this probably takes away your concerns.
Yes.
Okay, so using this axiomatization, using dagger Frobenius structure, we can give this proof of the teleportation. Okay, so now the other protocol, the state transfer. So this is the same idea. What we have to do is to look inside the boxes and try to describe the projectors, the measurements, using the material that we have, that is the unitary transformations and this copy and so on. And it turns out that here, this measurement is a parity measurement. And this parity measurement can be described as follows, just by, so you apply here a unitary transformation. So there are two possible outcomes. So here x is 0 or 1. In fact, F0 is nothing but the identity. So if you obtain 0, then what you apply is just the co-copy followed by the copy. And if the outcome is 1, the projector which is applied is this one where f of x is a permutation, is just a Pauling operator x. Okay. So here f of x is either the identity or x. So we can describe this parity measurement like this, and this measurement in the diagonal basis can be described as follows, using the delete and the co-delete. Okay, so the delete is not a physical evolution, however we can use it in order to describe a projective measurement. Okay, so
just a comment on that, I think one nice way to think of that is to think of it a many worlds thing at that point. So think of there being many planes to the screen. And at that point where you rip that box, the screen bifurcates into 4 sheets, and the diagrams continue on each sheet separately. And then the task is to prove that on each sheet the final thing is what you want to get out.
That's why quantum computing people like many worlds interpretation.
But the many worlds fits into the diagrams. That's what I'm trying to point out. Into it by a many-sheeted approach.
I just thought it spoiled.
You don't have to assume all the many worlds actually happen. You just have to make sure you take care of each possibility.
Yes.
And it makes it easy.
I know it's different for lot. You could use a different.
It makes it easier to get grants from FQXI too.
So we have 2 measurements which are described here, and here the correction, the unitary transformation you have to apply is f of x. That is, if the outcome here is 0, then you apply just the identity. If the outcome is 1, then you apply x. And we have something similar here. If you obtain 0, then you probably apply the identity, and if you obtain 1, you apply something else. Okay. So this is the description of the state transfer in the language. Okay, so now, so here we don't care about the state of this qubit after the measurement. So here we can remove this part, since we don't care about the state of this qubit, and we obtain this diagram. Okay, so now the objective is to prove that this is equal to identity. So the first thing that we do, we use the fact that f of x is a unitary transformation, so f of x followed by f of x dagger is equal to identity. Okay. Then, I have to see. Here we have some properties for f and g. It turns out that f of x is a permutation. It's a unitary transformation which is a permutation. And moreover, g of y is a phase, a unitary phase. Unitary. So we have these additional properties for the maps f and g. So we will use these additional properties. So here, from here to here, we use the fact that f of x is a permutation. So here we can just remove this map. And from here to here, we use the fact that g of y is a phase, so we can move the phase through the dot. So we can move g of y from here to here. And here there are 2 steps. First, we use the fact that g of y is a unitary transformation. So here we take the identity. And as before, here we use the comonoid and monoid equations properties to obtain the identity. Okay, so we can derive a proof of the state transfer in this language. Okay, so another interesting property is so we obtain a proof for both teleportation and state transfer, but if we look at the proof, we can see that we have a structural connection between these 2 protocols. That is, if we don't care about the classical outcome of the measurements and so on, we can sum up the teleportation as follows. So the teleportation, we have the integrated state at the beginning and the measurement, so we can abstract the teleportation as follows. And the state transfer can be abstracted as follows. And it turns out that the connections between these 2 protocols is just the Frobenius equation.
You didn't use your isometry condition.
Sorry?
You didn't use your isometry condition.
Isometry. No, you're right. Okay, so that's. Okay, we have this. This structural. We know how to derive the teleportation from the state transfer and vice versa. Okay, so now I want to compare this approach, what I've presented, with the original approach by Bob and Samson. And it turns out that they used in their original paper, they used dagger compact structures instead of dagger Frobenius structure. So now I want to compare these two structures, and in fact we'll see that the main question here is to know whether the dagger Frobenius structure refines a dagger compact structure. Is it a refinement to use a dagger Frobenius structure, or is it just two different structures? Okay, so let me start with the definition of this dagger compact structure. So we have seen before with the dual something which is like the same. So we have dagger compact structure if we have an object A and morphism epsilon A from A tensor A star. A star is the dual of A to I, which satisfies this equation. So here this is epsilon A, here this is the dagger. Notice that here we need this permutation of the qubits in order to for the type checking. Okay.
Should you have a sort of down pointing arrow on the for the second thing of EA?
No, at the moment everything is from the bottom to the top. It's just A star, and here it's A. But okay, so we need this condition. So an example, in fact, this dagger compact structure is an axiomatization of the inner product. So if we take our favorite example of finite dimension Hilbert spaces, we consider H star. The dual of H is the conjugate space here. Okay, consider that H star is the conjugate space, and then epsilon H is defined as follows. So epsilon H is nothing but the inner product. Okay. But it turns out that the inner product is not linear, it's sesquilinear. And here the idea is to use this dual H star in order to make the inner product linear. If we look at the map from H tensor H star to C. Okay? So these compact structures can be used in order to have an axiomatization of the inner product. Okay, so now we can define the dagger compact closed categories, which have been originally defined in the paper by Samson and Bob. So we have a dagger compact closed categories if we have a dagger compact structure for every object, and moreover if we have the following coherence condition, which says that epsilon A star is equal to epsilon A up to a permutation. So if you look at this condition, and if you have in mind that this is an axiomatization of the inner product, it probably reminds you that the equation that the inner product of yx is the conjugate of the inner product of xy. So conjugate comes from the start here, and here we have the permutation of two inputs. Okay, so this is the definition of the dagger compact closed category, and it turns out that we can extend the graphical language of the dagger symmetric modular categories to the dagger compact closed categories, and the main idea is that when we have a star, then we use an orientation from the top to the bottom. Okay, and this morphism epsilon A is depicted as follows, just a cap with a good orientation. Okay, this one to this, like this. So we have the same kind of notation for the dagger of epsilon A, for epsilon A star, for the dagger of epsilon A star. Okay, so we use this notation. So now we have some orientation in different ways. And the coherence condition says that, so here this is this one, okay, corresponding to this one, which is that epsilon A star is equal to epsilon A up to the permutation. And here this is the compactness condition. And in fact, using these conditions, you can see that whenever you have a wire, you can always yank it. Okay, here, yank it, and here this is the same. Okay, so and we obtain this graphical language for dagger compact closed categories. Okay, moreover, in order to have a planar representation, it's useful to add another condition, which is the strictness. We say that dagger compact closed category is strict if the compact structure preserves the tensor product. More precisely, it means that the dual of A tensor B is B star tensor A star. Okay, and epsilon of A tensor B can be obtained using epsilon A and epsilon B as follows. Okay, and it turns out that when you have this condition, then we have a planar representation. This is why we use this. Okay, so now we're ready to compare these two structures, dagger Frobenius structure and the dagger compact structure. So the first result is that whenever we have a dagger Frobenius structure, then we can construct a dagger compact structure. And the construction is here. That is, so you have the dagger Frobenius structure, you consider the co-copy or the multiplication, and then you erase the outcome, and you obtain something from A tensor A to I. And it turns out that here we have a dagger compact structure. The proof is here. So in order to prove that this is a dagger compact structure, we have to prove that this is equal to the identity. So we use the definition. So we obtain this. Then we use the fact that here we have the commutativity. And here, this is similar to the proof of the state transfer. Here we use the Frobenius equation. We obtain this. And then using monoid and comoid properties, we obtain the identity. Okay, so whenever we have dagger Frobenius structure, we have a dagger compact structure. But an important point is that the dagger compact structure that we obtain is self-dual. It implies, it forces the dual of A to be itself. And so it means that the dagger Frobenius structure refine self-dual dagger compact structures only. That is, if you have a dagger compact structure which is self-dual, then you can decompose it, refine it using dagger Frobenius structure. But if it is not self-dual, you cannot use this decomposition. And it turns out that so it's quite restrictive, and it turns out that the interesting dagger compact structures that we are using are not self-dual. In fact, we have seen that the dagger compact structure can be used as an axiomatization of the inner product, and in this axiomatization we use the dual in order to represent the inner product as a linear map, and this is a very important point. So we cannot represent the inner product using a self-dual dagger compact structure. So this is an important point. And moreover, I've just talked about the planarity. It turns out that in order to have a strict dagger compact closed category, that is a dagger compact closed category with planar representation, planar diagrammatic representation, then we need this equation, that is the dual of A tensor B is B star tensor A star, whereas if the dagger compact structure is self-dual, we have A tensor B. Okay, so in this case, we cannot have a strict dagger compact closed category if it comes from the dagger Frobenius structure. Okay, so the idea is that in general, if we have both an a priori non-self-dual dagger compact structure and a dagger Frobenius structure for the same object, then the object A has two duals, the dual A star, which comes from the dagger compact structure, and since we have the dagger Frobenius structure, A is self-dual. Okay, this is the property that we have seen before. Whenever we have the dagger Frobenius structure, A is self-dual. So in this case, we have two duals, and it turns out that according to Kelly Laplace, these two duals are isomorphic. So the idea is to, in this case, to make this isomorphism between A and A star explicit. And we obtain the following structure, the dagger dual Frobenius structure. So which is the dagger Frobenius structure plus a dualizer that is a morphism from A to A star, which is unitary.
Are you asking for this dualizer as an axiom, or are you constructing it from a compact structure?
Okay, so yeah, here it's not clear. So if you have the compact structure and the dagger Frobenius structure, you can construct the dualizer. But here the idea is to have an axiomatization with the dagger Frobenius structure and the dualizer, and we will construct the dagger compact structure. Okay, the compact structure is derived from the dagger dual Frobenius structure. So, and this is the construction. So the first property is that if we have such dagger dual Frobenius structure, then we can construct the following morphism epsilon A. So we apply the dagger of the dualizer, so from A star to A, and then we apply the rectification and the delete. And it turns out that the morphism that we obtain forms a dagger compact structure. The proof is here, so it's similar to the previous proof. There is just one more step, which is that here at the beginning we use the fact that the dualizer is unitary. Okay, so we have this dualizer in order to have here A star instead of A. Okay, so whenever we have dagger dual Frobenius structure, we have dagger compact structure, but the other way around is true as well, which is that if we have a dagger compact structure, it's possible to decompose this dagger compact structure into a dagger dual Frobenius structure. And it's even stronger. What is this lemma is stronger because here it says that whenever we have a dagger compact structure and a dagger Frobenius structure for the same object, this is what I said before, then you can construct the dualizer as follows. And here the proof is that this dualizer is a unitary transformation. Okay. Let's go to the details. Okay, so what we have to have in mind is that any dagger compact structure can be decomposed using this dagger dual Frobenius structure. That is using this dual. Okay, so now we define the dagger compact closed categories with bases. So the idea is that for any object we have this dagger Frobenius structure where we satisfy some additional properties, and in order to have coherent in the name of the category, we have to prove that this is actually a dagger compact closed category. So we can do it. So we already know that here, if we use this construction here, we have a dagger compact structure, but we have to satisfy the additional equation, this one associated to this one, and here we have the proof that it works. Okay, and so now we can extend the graphical language to the dagger compact closed category with bases, and the main idea is to represent this dualizer as a dot, just as a dot. Then the decomposition of the compact structure is given here, so we're using the dualizer, the copy, and the delete, and we have some additional clearance condition. I want to go to details, and we can also make this dagger compact closed category stripped, that is, in order to have this planar representation. Okay, don't want to go to the detail, but we have seen that there are two problems with the decomposition of a dagger compact structure with a dagger Frobenius structure. The first problem is the star, is the fact that A is necessarily self-dual, and the other problem was the planar representation. So here we can see that using this dagger dual Frobenius structure, we can have this planar representation. Okay, so now I'm coming to the comparison of the two approaches. for the example of the teleportation. So it turns out that this notation of the dualizer as a dot is particularly interesting because we have this kind of property. That is, here, all these notations are equivalent. That means that we can just move the dot through the wires. So here, this is the shortcut for this. In the middle, this is this. Okay. Here, this is the dualizer, and here the compact structure. Here the dualizer, and here the compact structure. And it turns out that all of them are equal. So we can move the dot. And if we start with the description, the categorical semantics of the teleportation that I've presented before, where all the orientation are from the bottom to the top, so it's physical flow, because with respect to the time evolution. Then starting from this representation, we can move the dot using this, we can move the dots, the two dots, using these equations. Here we move the dot like this, and here like this. Then we use the unitarity of the dot. So we can just remove this part, and we obtain this representation in which the flow of information is pointed out. Okay, that's it. So, yeah, thank you.
Any questions?
Is the dualizer that's
Highly basis dependent.
No, because this is basis dependent.
Usually compact structure.
Yes, but the idea is that you start from something which is basis dependent, and you obtain something which is basis independent, but in order to do that, you add a morphism which is also basis dependent. This is just every morphism, if you take any of these morphisms, all of them are basis dependent, but if you combine them, you obtain something which is basis independent.
The whole idea of capturing a basis by Frobenius algebra is utterly unnatural, so to say. So you really want to exploit unnaturality to get something, to get your hand on this. So it's very uncategorical in a sense, but that's exactly what you use.
I mean, okay, just I do like very much because it really shows me how you categorical language is connected to physical flow of information. And that's quite important, I think, to just this is a very good observation. Other questions?
You mentioned planarity a couple of times. What's the significance of the planarity? Because the way you described it, you kind of imagine, in general, all these diagrams would be located in ordinary physical space, and the planarity, and it could be very non-planar, or like something.
Okay, so first the planarity for diagonal compact closed categories is just that you can represent it using a planar diagram, because you know that when you decompose this compact structure of A tensor B, you obtain something which is planar, so it preserves planarity. Okay, so the notion of planarity for the other case, that is the diagonal compact closed category with basis, is not really well defined, because it turns out that whenever we have this copy, we obtain something which is not planar. However, if you just look at the compact structures, then we obtain compact structures which have a planar representation.
But it's not the case that every morphism in category has a planar representation.
In a diagonal compact closed category, no. No, but if you start with a planar representation, and if you apply the equations, these kind of equations, then you still have planar representation.
Right. So even if you've got a very complicated overall situation, it's not at all planar. The significance is what you're doing preserves such planarity as well.
So what is the link between 2D TQFT?
Sorry?
What is the link with 2D TQFT?
I don't know.
It's basically the same thing, except for that you don't have this isometric thing. And do they consider these? They don't consider. They need orientation, I guess, for the duals.
The Frobenius algebra is just entering as a device to have a basis. So there's no information in it really, other than just recording a basis. Whereas in a 2D TQFT, without having that no loops rule, you have information in it because it's got some numbers there.
Right. This just says those numbers are 1.
Yeah. So it's a trivial 2D TQFT, but it has that one non-trivial fact that it does record the basis. So it's not, yes.
But I mean, the point of the 2D TQFT is if you tile some polygon in some way, it's independent of the tiling. So
All your quantum errors are just one. It gives everything just one.
No, it'd be
No,
n.
yeah, but
sorry,
if you-
dimension.
the
dimension will be kicking around somewhere.
But it's invariant under change of triangulation.
That's what I'm saying. So if you have a disk, it just depends on the boundary of the disk, and not the detail of the inside. But that's somehow what your calculations are saying here.
You must be careful with the open. Don't confuse the open. Yeah, because the lattice model you're doing there is the open string model, and then you got to afterwards go to the closed string.
We're just doing TQFT with a disk. Two-dimensional disk. And then it just says that it just depends on the boundary data, not on how you cut up the disk inside. But that's somehow what was previously around.
Have you done it in the case when you add a handle on the surface? So it isn't planar, it's higher thickness?
No, it's not.
But I think there has been a very long discussion last 2 weeks on the Categorical Cafe and one of John By's blog trying to see connections between this sort of stuff and TQFT. I think Bruce was very involved in that and Jamie too. So but they've been sort of.
Okay, so let's go speak again.